All right, welcome back. In this example, we're going to apply work to a pumping problem. These are very classic. In a lot of ways, this is similar to the previous examples that we've talked about, but also it's very different because in this case, we're dealing with a three-dimensional material, liquid. The good news is, though, the general concept and technique is exactly the same. What you may notice is in these kind of examples, we're going to attack the work just like we did with these cables and chains. But then the work of dealing with this three-dimensional object or this liquid inside here is going to be very similar to the solids of revolution that we've seen recently. All right, so here's our context. We have a conical fermenter that has a height of 3 meters and a radius of 1.5 meters. It's filled with wort. By the way, wort is just what you'd call like this stew before you get out beer in these fermenters. This has a density of 1,010.5 kilograms per cubic meter. That should make sense. By the way, and you'll see this in examples, water, so pure water, has a density of 1,000 kilograms per cubic meter. So this has a little bit more stuff in it, make it a little bit more dense. So it's filled to within a half a meter of the top. I'll deal with that towards the end when I draw this in. The question is, as we should expect, is how much work is required to pump all the wort out. Not only that, but to a height of 2 meters above the fermenter. And so we're not just trying to get this wort out of here, but we need to raise it up probably to get it to another tank or something like that. Now, again, importantly, the general attack is going to be exactly the same, though you'll notice there's a little bit more complexity in each of these steps. So first things first, as always, we're going to get a force function. Let's remind ourselves of this. Is that force is always the mass times acceleration. Acceleration, as we've seen it, as in this case, the acceleration is the effect of gravity pushing down on this. Mass, by the way, let's just clarify this before we move forward, is density times volume. So of these three pieces, I have the densities been given to me right here. Acceleration, I know, is the 9.8 meters per second squared of gravity. What I need to deal with is the volume, and specifically what I want to think about here is I'm creating a force equation as we've previously done for each of these ith intervals. So what I need to do right now is define these intervals and these slices that I'm looking at. First and foremost, one trick that I'm going to do, and this is kind of the reverse of the solids of revolution, I'm going to superimpose an XY axis on this object right here, just to make it a little bit easier to do my calculations. What I'm looking for in this case, so I'll call this X, I'll call this Y. This height right here obviously is the same as that height. I then want to define these slices, and so I have a slice. Let me just draw in a little slice here. What I'm going to do are take these slices, and looking at this is the idea of a washer. You'll know that this has a thickness of Y or delta Y. So I'm looking at these washers, and what my goal is and when I'm creating this force function, is for each of these little washer slabs, I want to define this function based on the density times the volume is the work I'm doing now, and times acceleration. So we've seen a lot of examples like this in creating this slice right here. There's a couple different ways I can attack this. One way I can attack this is by using this ratio right here of 3 meters to 1.5 meters. I can think about triangles right here to create an equation for if I go a certain height right here, I'll get a certain radius. But actually either way, just to make this statement right here, I'm thinking of this slab as being on the ith interval, and I'm thinking of these vertically for many different reasons, but specifically each of these slabs has a delta Y. And so I want to think of this slab right here. I'll call this Y sub I. Really kind of technically I should do y sub I star just for this sample point on the ith interval. But just because of all the writing I'm going to have here, having that extra little star is going to make it confusing. You all get it at this point. You've seen it tons of times at this point. But anyway, so I have this slab right here. And again, I've talked about I could use similar triangles. There's no problem. But actually, I superimpose this on an XY axis, so I could use a little bit easier technique. What I'm going to do is define this radius right here based on this line. So I'm going to find the equation of this line, this vertical line right here. The equation of that vertical line and the x value of that line will determine the radius. The equation of this line is actually pretty dang easy if I realize that the line I have here, because I've superimposed this onto the origin, so this goes through 0, 0, and the point 1.5, comma 3, and that should make sense because I go over 1.5 units because that's the radius of this fermenter and has a height of 3 meters right here. So I have a y-intercept of 0. My slope in this case, will I go up twice as far as I go over, and I could do the work to actually find that, but it's really straightforward, is that the slope of this line is 2, and so the equation of this line is y equals 2x. Importantly for the work that I'm going to do is that this radius is determined by the x value here, obviously, right? As we go up and down this. And I want to write these in terms of y. So I'm going to rewrite this real fast as x equals y divided by 2. So I've gone a little bit quickly through that, and there's a lot going on right here, but this is stuff we've previously seen. This is just like a kind of a solid revolution analysis within this problem real fast. But to describe this again, so I've superimposed this here. What I'm doing is trying to find one of these cross-sectional areas, right? I have this cross-sectional area that I'm going to multiply by this delta y to give it a thickness of volume. In this case right here, to define the radius, I'm going to use the definition of this line right here, which defines the length of this radius for any of these slabs. I'm writing it as x equals y over 2 for 2 reasons. One, because this distance is an x value, so this will be my radius. And also because it's a delta y thickness of this I'm describing, I want to write these all in terms of y. And so what that means is for this ith interval right here, the volume of the ith interval is pi times the radius squared. And in this case, it's yi divided by 2 squared. And again, this yi is the height that I've gone up, times the thickness. So this is the radius, or this is the area of the cross section, and then I'm multiplying it here by the thickness to get a volume. All right, let's now plug all of this information in. Again, we had the density and the acceleration that was given in the beginning. We've now done the work to find this volume. So our density is 1,010.5 kilograms per cubic meter. And then our volume here is described by this. So this is pi times yi over 2 meters squared times delta y meters. And the acceleration due to gravity we know is 9.8 meters per second squared. And then just to clean things up a little bit, the only tricky part is squaring this part. I'll get a yi squared over 4. And then I'm going to multiply these two together, divide by that 4. And just for kicks, I'm going to leave the pi out here. It won't really matter at all. But let's see. I got my force on the ith interval is that times that divided by 4, which I get is 2475.73. And we're multiplying that by pi, and I get a y squared delta y. And just for kicks, you really don't ever have to do this, but this helps you know that you're doing this right. So force, again, in the metric is the Newton. And so just to make sure that I am in Newtons, that I didn't screw something up, I have kept all of my units here. So let's just check these out. So I got meters squared here when I square that, times meters, that's cubic meters. That will cancel with the cubic meters down here. So those cancel each other out. And so then I get meters over seconds squared times kilograms. I'll just rewrite that as meters times kilograms per second squared. And this is, if you remember, is the units for newtons. So I've got my force function for each of these little slabs that I'm looking at right here. I have the density, I have the volume, which is by far the hardest part with these, and then my acceleration right there. I've confirmed it's in newtons, so I have 2,475.73 pi y squared times this delta y, and then in terms of newtons. So let's now work on the work part of this. And as always, really most of the work on these problems is finding this force function. The work is just multiplying that by the distance, and it won't be very complicated here, but we got to do some analysis. But we'll do here. So we have the work for the ith interval is going to be the force of the ith interval. So let's write that in right here. So that's already been done. Y squared delta y, and then I'll just leave off the units this time, because I know that if I have newtons and I'm going to multiply by distance in terms of meters, I'll have newton meters or joules in the end. So the distance is next. What I need to do is analyze for each of these slabs. I'll have calculated the force. I need to figure out how far they need to go. And so what I'm looking at is how far do I need to pump this slab right here? Well, if you remember in the problem right here, we want to pump it to 2 meters above the fermenter. So let's think about there being this little pipe inside here that we're going to pump up to. And again, it's probably going to go over, but the real work is just getting this up and fighting gravity with this pipe, with this slab right here. So let me just think. So this is going to be 2 meters above. So in the end, I want to get to this height right here, which means, by the way, so this is an important thought, is that the entire height, or the height I'm trying to get to, is 5 meters. So I'm just going to write that here on the side so I can analyze this. So the slabs I'm looking at are here. They're yi off of the x-axis here. So this is their height, as has been determined in this formula right here. So I have this slab at this height. The question is, how far then do I need to pump it? And this is important to note, is that the slabs lower down, there's further for them to pump, so the distance will change. Towards the top, we're not as far, but we have this yi height. If I want to get all the way up to 5, it's just the difference between 5 and this height right here. So the height to pump this will be this height of 5, and then minus the height that I'm looking at this slab. So this will be 5 minus yi is the height that I'll need to pump each of these, or the distance. And so this will be 5 minus yi. So there we have it. We have our force function that we defined based on this volume and the density and the acceleration. And then to get the work for each of these little intervals, we've now applied the distance. Again, the distance will change because the stuff higher up has less of a distance to go than the stuff further down. Here I have that. Again, the 5 came from the 2 meters above the 3 meter tank right there. Now what I'm going to do is just rewrite this and clean this up a little bit. I'm almost ready to integrate, so I'm just going to combine some stuff, make my life a little bit easier in the next second. Let's multiply this and distribute this 5y minus yi into this right here. And so I'll write it like this, squared minus yi cubed. So I'm multiplying that in here. I have pulled this out because we're going to be doing integration, and that constant will come out. And then I'll put this delta y right here on the outside. So as always, I've done all my analysis just through these little snapshots, these little slabs or these little washers that I'm doing here. I've created a force function and then right after that create a work function. Our job now is to use this limit sum or integration to find all of the work. So all of the work of pumping the wort from y equals 0. Now this is an important thought right here real fast. So what I'm looking for, my bounds are where this wart is. If I go back up to this original picture, importantly is this statement right here of 1.5 meters from this top. What that means is the whole fermenter isn't full. It's full to right about here. So this is where the wart is down here. And so when I'm doing this, I'm defining my y, so my bounds of my integration here is from where the wart starts, so at a height of 0, and it goes up to a height, a y value, not of 3, but of 2.5 meters, because I don't have the whole thing full. So from y equals 0 to y equals 2.5. So I want to just marinate on that point just a half second as finding this bound right here. So the 3, which is the 3 meters is the height of the fermenter, absolutely played a role in defining the size of these little slabs right here, because the general slab was determined by the height relative to the width right here, to this radius. That created this equation and affected the size of each of these little volumes. But the fact is, as I'm defining this work, I'm defining the work on an actual liquid. When I go to integrate, this full thing isn't full of liquid. So I'm not going to integrate from 0 up to 3. I'm going to integrate from 0 to where the liquid that I'm determining the work for stops. And finally, for that same reason, I'm not integrating up till 5 meters or something like that, because the water doesn't rise there. When I do this and put this into my integration, these are my bounds, because these are what limit where the water is. Not water, work, but you get the idea. So here we go. We're going to compute the work by integrating all of these little works over this interval. And so I have from 0 to 2.5. I have my definition here, so this is 2,475.73 pi times 5y squared minus y cubed. And then that delta y becomes a differential of y when I take the limit as n goes to infinity. And as with all of these work problems, the real hard part is actually getting to this step. Actually computing this integral is really straightforward, so we'll just do this quickly. So this is a constant that comes out, so this does not affect the integration in any interesting way. I integrate this, and I get 5/3 y to the third minus 1/4 y to the fourth. And we're going to evaluate that from 2.5 or from 0 to 2.5. Importantly here again is that when I plug in 0, nothing happens. So this comes down to just plugging in 2.5 here and evaluating. And when I did that, I computed that this is going to take 126,590.74 Newton meters or joules. So just a real quick review. We've actually reviewed already as we've been going through this. These can feel intense, but really these are only just a little bit more step from what we've done previously, and it's connecting something we've done with the solids of revolution, right? So it's a little bit more complicated than these cables and chains, but not really if we got good at defining those little slabs right there. So first things first is to focus on the force. So force equals mass times acceleration. The acceleration almost in every context we have right here is acceleration due to gravity. Again, remember, if you're dealing with pounds, you don't have to add that acceleration in because pounds already includes that concept. Mass is computed by the density of something times the area or the volume. This is a three-dimensional object in this case. So this density is a three-dimensional density and the volume's a three-dimensional units. Density, by the way, if we're just pumping out water, which is a common thing that we're going to do, is always just 1,000 kilograms per meter cubed. If it's a liquid that's not water, they should give you the density of that liquid. You multiply that. So again, these two are given in the problem. All I need to do is compute the volume for these little slabs. And there's many different ways of doing these with the objects you have. Get creative. Maybe find a line, something like this, or just somehow draw in the picture and describe that cross-sectional area, multiplying it by this delta y or delta x, depending on how this is leaning. Once you have that definition there, you're simply going to throw that into the force equation multiplied by the density and the acceleration. The last step, so it's a majority of the work. It looks intense, but those are the steps broken up. And then you need to say, for each of those slabs, what is the problem telling me about the distance it needs to travel? Because work is always the force times the distance.